This P4 video is talking about resultant force. I'm going to concentrate mainly on the descriptions with no complex calculations. There'll be a separate video following that will cover that one. So first of all, what is resultant force? Well, in order to find resultant force, you need to add together the individual forces on an object caused by real interactions, and you need to take into account the direction. So the easiest way to illustrate this is to show some examples. So we'll start simple and get a little bit more complex. So first example, an object here with two forces on it, 6 newtons and 3 newtons, both pointing to the right. And what you can do is you can put the arrows that represent the forces one after the other, remembering that a longer arrow means a larger force, and see how long the arrows in total that you get going from the start of the first one to the end of the last one. And that makes sense here that it's 9 newtons. That should be fairly obvious. They're both pushing in the same direction, and so they're going to reinforce each other and give you a larger total force. If you have forces pointing in opposite directions, then the small force will partly cancel out the larger one. So in this case, we've got 6 newtons to the right, 3 newtons to the left, giving us a total of 3 newtons to the right. So that's a couple of examples just in one dimension, so just left, right. You need to be able to cope with two-dimensional versions of these, but there's always going to be one direction that will cancel. So let's have a look at this example. So we've got 4 forces now. And you will quite commonly get 4 forces on an object. Things like cars and bikes on roads will tend to have 4 different forces on them. And again, we can put them end to end. Doesn't matter which way we do it. So start with the upward force and then following the one to the right, the one down, and the one to the left. And then we go from the start of the first arrow to the end of the last arrow, and that tells us our resultant is 2. Okay? Obviously, if you look at that carefully, you can see that the up and down 2 newton arrows, we can fade those out now, will cancel each other out. So that basically turns it into a problem that's just like example 2, where we only had the left-right forces, and then it's just the 3 newtons worth of the 5 newton forces cancelled out, leaving us with 2 newtons to the right. When you're writing down resultant forces, try to include the direction, because force is a quantity where direction matters. There's sometimes a space for it in an answer, so it'll have a value for the force in newtons and a space underneath for writing the direction. Even if it's not there, try and write it down if you can. It's helpful to do that. Okay, so that's what resultant force is. We then need to understand why it's useful. I'm going to start slightly weirdly with what it doesn't do, because this is a big misconception that people have. Okay, resultant force doesn't tell us how fast an object is moving. It doesn't tell us what direction an object is moving in. If you take those two things together and remember that speed and direction added together gives us velocity, then it doesn't tell us the velocity of an object either. Resultant force is all about telling us how the motion of an object would change. Okay, so it does tell us how the speed of an object is changing. It tells us how the direction an object is moving is changing. So in other words, it tells us how the velocity of an object is changing. And it's this word change that you've really got to try and remember. If an object is not changing speed or direction, then there is 0 resultant force on it. There could still be individual forces, but they will all cancel out to give us 0. Okay? Let's look at this with some examples then. So, case 1, resultant force is pointing in the same direction as the motion. So if we have a car on a road, wonderful artwork, I know, we've got the downward force being the weight of the car, an upward force from the reaction force of the ground on the wheels, and as long as the car is not starting to fly off into the sky or starting to sink into the ground, then those two will be equal. Okay? And obviously, because the car's got 4 wheels, there'll be 4,000 newtons on each wheel on average. Could be a little bit more on one and less on the other, but on average there'll be 4,000 newtons on each wheel. Okay, giving 16,000 upward in total. So those two cancel out. It's like example 3 from before. A motive force or a driving force comes from the engine, and that provides 3,000 newtons. I know that you are supposed to know for interaction force pairs that the force is really applied from the ground onto the tyre, because the tyre rotates and tries to push the ground backwards, and therefore from interaction pairs the ground pushes the tyre forwards. You will often see this motive force just as a forward force on the car without worrying too much about the fact that it comes from the tyre. So don't get confused if you see that in a question. And then some air resistance or drag pointing in the opposite direction to the motion of the car. So this car's moving to the right because the air resistance is pointing left. That actually tells us that. So again, the resultant force is 2,000 newtons, but how does that affect the motion? Okay, we've got 2,000 from the 3,000 forwards, 1,000 of it cancelled out by the drag. Well, because the motion is to the right and the resultant force is to the right, then the car will increase speed. Okay, if the resultant force points in the same direction as the motion, that causes an increase in speed but no change in direction. Case number 2 is the opposite of that. So we've changed around the forces a bit on the car. We've still got a driving force forwards, a motive force of 500 newtons, but now the air resistance is very large. So this might happen if you were driving along and suddenly took your foot off the accelerator. It would reduce the force of the engine, and hopefully you all realise what would happen there is that you would slow down. So again, we've got the car moving to the right. This time the resultant force is 2,500 to the left, and that causes a decrease in the speed. So every time the resultant force is in the opposite direction to the motion, there will be a decrease in speed, but again, no change in direction. So, case 3, how do we get the change in direction? And a useful one for looking at this is orbits. So, I've got a picture of the Earth in the middle there. I'm going to put the moon around the outside. I realise the pictures aren't correct because the Earth is oriented incorrectly, and the picture of the moon I'm going to use is what it would look like from Earth, but bear with me for artistic license. Okay, so at all points in the moon's orbit, the only force acting, really, significant force, is the gravitational force due to Earth. So in that case, if there's only one force, then that force will be the resultant because there's no others to add in. So if we put the moon in place there, then the Earth is pulling the moon towards it. So that's why the yellow force arrow is off the left. Okay, and wherever we put the moon, okay, the Earth is pulling the moon towards its centre. The blue arrows here represent the motion of the moon. So the moon is moving along the green circle. It's approximately circular orbit. It's very slightly elliptical. And you can see that at every point around its orbit, the blue arrow showing its motion is at right angles to the yellow arrow showing the resultant force. When you have the resultant force at right angles to the direction of motion, then there's no change of speed, only a change of direction. So that makes sense. The moon orbits at a constant speed, right? But its direction is constantly changing because it's moving in this almost circular path. Note that both of the situations where you have the force lined up with the direction of motion, the force at right angles, you could regard as a change of velocity because velocity is direction and speed combined. Okay, so always the resultant force, if it's there, will cause a change in velocity. We're just narrowing down on the exact change that we're going to get. Okay, so how about a mixed situation then? So let's look at a different type of orbit. Again, yellow arrow is a resultant force, blue arrow is the speed and direction of the motion. So the longer the blue arrow is, the faster the object's moving. Let's look at an asteroid. Some asteroids have orbits approximately this shape. Comets as well would be another example. So we'll put the asteroid in here. The resultant force is quite weak here because the asteroid's far away from the sun, so gravity is weaker. And it's moving quite slowly. Okay, this is what asteroids do at the extremes of their orbit when they're furthest from the sun. So the blue arrow is pointing up, again, right angle. So this is a bit like the moon situation. But if we move the asteroid round its orbit, okay, then we will see something different happening. In its situation we've got here, again, forces at right angle to the motion, so there's only a change of direction. But if we put the asteroid here in its orbit, the yellow arrow is pointing again towards the sun, because that's the way the asteroid is being pulled by the gravitational force. The blue arrow is pointing along the green path that the asteroid is taking. So here we haven't got one of our particular situations where the arrows are lined up or they're at right angles. It's a mixture of the two. Because the yellow arrow is pointing slightly forwards in terms of the fact that it's pointing in roughly the same direction as the blue arrow, there will be a speed up. Because it's also pointing slightly sideways, it will also cause a change in direction. And you can see that from the shape of the orbit. Okay? And obviously, as the thing is speeding up, as it gets closer, then the force increases and the speed increases, and we have an asteroid there that, again, is having a change of speed. Still, speed is increasing because the blue arrow is at least, they're almost at right angles, but the blue arrow is at least sort of still pointing in the same direction as the yellow arrow in terms of speeding it up. But it's mostly to the side now, so there'll be much more of a direction change. And you can see that because the green line is curving more steeply. There's a big direction change happening in the path of the asteroid here. And then if we go past the point of closest approach, where the asteroid's going to be going fastest, and look at it as it's moving away from the sun, then now we can see the yellow arrow is at least pointing partly back in the opposite direction to the blue one. And so it's going to be slowing the asteroid down. But again, because it's pointing partly to the side, then it will also be changing its direction. So if you're on these mixed situations where the resultant force is not pointing at right angles or along the path of the motion, then you'll get both, a change of speed and a change of direction. Okay. And of course the final case, almost the simplest one, no resultant force. So if I have an asteroid drifting through deep space, it's moving, because we can see from the blue arrow it's got motion, but no resultant force on it, it will keep going in the same direction and moving at the same speed. There will be no change in its speed and direction. A big misconception here is that objects with no resultant force must be stationary. That is not true. Okay? Most examples of objects on Earth, it is true for, because there's always friction on Earth. Okay, and so there's always going to be a set of balance forces there producing zero resultant, which will mean the object is stationary. But there are some examples, so like an air hockey puck, if you slide that across an air hockey table, it will basically keep going in the same direction at the same speed because the friction is so tiny there's effectively no resultant force on it because its weight is being balanced by the air pushing up on it. Okay, it only changes direction when it hits something else. So there are examples with very low friction where you can see objects with no resultant force that are moving. Okay, right. Let's just have a look at another really common question that they ask. This has been asked a couple of times in different ways in the exams in the past. Object being thrown up in the air. So take a ball and throw it up in the air. And we're going to ignore air resistance to make this a little bit simpler. Well, when you do ignore air resistance, the only force acting on that ball is going to be gravity. So there's the path of the ball. We're moving it from left to right as well. Okay, we've thrown it up. It's got to the top of its arc and come back down again. So a big misconception is that the force kind of follows its direction of motion. We have to think about what's actually causing the force. The only thing causing the force on that ball, if we don't have any air resistance, is gravity. And gravity pulls the ball down towards the ground. So all the yellow arrows on those balls are pointing straight down. And because the weight of the ball is constant, then they're all the same size as well. Okay? So how is the ball moving? Well, we know that it's going up quickly to start with, right? I'm ignoring the sideways motion here. I know that I've put it in a sort of like a flight path, but we're only interested in the up-down, so forget the left-right for the moment, okay? So the ball moves up to start with, very fast, and then it slows down as it moves upwards. At the top, it's stationary for just a second as it turns round and changes direction, comes back down again, getting faster and faster as it does so. And this makes total sense in terms of what we've just said about the effect of resultant force. You know that's what happens with the ball that you throw straight up in the air, right? Even if you didn't know anything about resultant force. But we have to make sure that it fits. Well, let's look at our examples. The first one here, the yellow force arrow is pointing in the opposite direction to the motion, so the speed is decreasing. That's what happens when you throw a ball up in the air. It starts fast and it slows down. Same for the second situation. At the top, okay, we've already said it's stationary for a moment. As it comes back down, the force arrow is now in the same direction as the motion, so it's going to speed up, which is exactly what happens. And that keeps happening as it comes on the way down. So that very apparently simple situation of a ball being thrown up in the air perfectly illustrates our rules about how resultant force can affect the motion. Okay, so to summarise then really quickly, to find the resultant force, add all the forces on a single object, take into account the direction. You mustn't start adding forces that are acting on different objects. That will give you a wrong answer. If the resultant force is not zero, then the object's motion will be affected. Speed will increase if resultant force is in the same direction as the motion. It will decrease if resultant force is in the opposite direction to the motion. And the direction will change if the resultant force is at right angles to the motion. And you can, of course, have a mixture of those happening if it's not exactly one of those first three situations. Okay? If the resultant force is zero, that means the object will continue moving at the same speed and in the same direction as it has been before. And that, I have to remind you that it doesn't mean that it's not moving at all. It may be, but it doesn't mean that it isn't moving.